Okay, so get started. Yeah, let's give what we mean by conditional probability. Now we did some probability trees and tables, but I can't quite remember. Maybe I did, maybe I didn't. Did we talk about this symbol in class before? I kind of feel like I told you about this. Yeah. Well, there's no harm in revising what it means. So this is well, I wonder if actually does anybody remember? Nobody? No? If? Give me a sentence.
B if not A.
No. Way off. Nearly. You just have it the other way around. If given B, probability of A. So it's a probability of A if given B. In other words, put simply, it's the probability of getting A given that you know B has happened. So you know B has happened, and you want to know what's the chances that A will happen, given that you know B has happened.
So it's like if it rains, and then how the probability of it not raining.
Yeah, so it's like what's the chances it'll rain tomorrow, given that you've just experienced rain today, as an example. So, we can do that as an example. So, what's the probability? Where's my pen gone? I can't see. What's the probability that it rains tomorrow, given that it rained today, as an example? Okay, once you have that, let's try and figure out a formula here. Yep. Got that? Yeah. Scroll down. Okay. So we did ones like this when we had our tables. So let me just give us an example to remind us of the idea. So let's say we have people who smoke. And let's keep it simple. We have 100 people in total. So smoke, don't smoke. Come on. Cancer, no cancer. Now, let's see. We'll say, how many will we say we have smokers? Let's say we have 40. Let's say we have 40 smokers and 60 non-smokers. And 35 people with cancer and 65 people without. And the total is, we can see, 100. Got that? So, should remember doing this. Probability of cancer here, what's that going to be?
40.
35 over 100. 35%. But we can all appreciate that's different if I said probability of cancer given that the person smokes, and the probability of cancer given that they don't smoke. So if we look among the smokers, what's the probability of cancer? 30 over 40. Yeah, isn't it? Smokers? 30 over 40? So 75%. And the probability of cancer if you're a non-smoker? 5 over 60. What's that? It's nearly 10%. It's about 9%, isn't it? Roughly. 5 over 60, is that about? No, it's not 9%, is it? Or is it 12%? Yeah, which is 8%. 8% roughly?
Yeah, 8.3.
Okay. Okay, we'll just say 8%. Can you appreciate that those three answers are very different? Very, very different. So for this type of example, it was critical to know this or to know this because it had a huge effect on the answer compared to not knowing it. Yeah? So and this is a common medicine thing as well. You know, like what's the probability of contracting a certain illness? You know, like what's the probability of, you know, a patient presents with heart disease, what's the chances that they'll also have type 2 diabetes? That's totally different than if someone just presents without heart disease, or you don't know if they have heart disease or not, you know? These are all quite different probabilities. So let's see how we calculated this one, for example. What did we put on the top? We put cancer and smokers, and then what do we put on the bottom? Smokers. So it was cancer and smokers over smokers. So if we would try to think this as a formula using sets, then the probability of A given B is the probability of A and B over the probability of B. So basically that's our definition, that's our formula for conditional probability. Yeah? So obviously that's important if you want to make note of that. And then we can have a look at using that for some examples now. Okay, you go. Yeah, okay. Have you talked about any illnesses in biology that perhaps have a relationship? No?
We did cystic fibrosis.
Yeah, but you at least mentioned it.
Yeah.
Does that have a relationship with anything else? And what exactly is the... That,
Cystic fibrosis is used in the labs so they can contract infections and stuff.
so would it be right to say if you have cystic fibrosis you're more likely...
Very
Very likely. Okay, well that's a good example. Let's have a look at that one then. Yeah? Okay. Oh, sorry, do you have this? Yeah. Wait a second, Mubarak. No. Too late. You come back for the second class then, okay? Right. Okay, let's have a look at an example. So, you'll have to give me some numbers, but we'll draw our Venn diagrams first anyways. So cystic fibrosis, is that an S or a C? A C? C. And pneumonia is an N. P. PN. PN. Oh. Oh, I don't like it. Oh, I don't like both. Right, cystic fibrosis and pneumonia. Okay. we'll have to estimate some numbers. So, did Colin say how many people have cystic fibrosis, or how common it is?
It's very common in Ireland.
Okay. How about we say 5% of people have it? So we'll get that. And how many people have pneumonia? Well, maybe 5% is too much, but anyways, we'll say 6%. Winter, perhaps. Okay, and then the last thing. So you said it's very, very likely that you'll get pneumonia if you have cystic fibrosis, or is it the other way around? That way around. So that is represented as this probability: the probability that you'll get pneumonia, given that you have cystic fibrosis. And you said it's very likely. So let's make it 90%, like this. So our job now is to complete the Venn diagram. So you remember the trick I said for this? It's kind of helpful if we can call the middle here x. So because we know that this is 5% of the population, and this piece here has to be 0.05 minus x, and this piece here? 0.06 minus x. Ooh, we don't know what this is. We know the total has to add up to 1. Okay? Now, I guess if you want, you can call this outer piece y. So the situation is we have 2 unknowns. But that's okay, because we can actually make 2 equations. We can say that the total here adds up to 1. And I've not used this piece of information yet. So according to the formula I gave you a moment ago, this is the probability of pneumonia and cystic fibrosis, which is x, over, and then what do I put in the denominator here? Cystic fibrosis, which we actually know. Yeah, true, it's this plus this, but we actually know what the total is here. It's 0.05. Yeah? And that should equal 0.9. Great, that gives us the x. What is that? 0.045? Yeah? So let's start filling in numbers. This here is 0.045, which means then this must be 0.005, which means this must be 0.055. Is that right? I think so. And the total adds up to 1. So what is the total here? Let's see. That is 0.05. 0.05 plus 0.055. 0.105, so I think it's 0.895 goes here, if I did everything right in my head. Someone's checking there? Yeah? Yeah, okay, good. Good. So now that we have the Venn diagram drawn, we could answer other questions like this. So you might say a patient has presented themselves with pneumonia. How likely is it that they have cystic fibrosis? So that's the other direction. What is the probability they have cystic fibrosis, given that they have pneumonia? So I want you to calculate this for me. You have all the numbers in the Venn diagram and you have the formula. So see what you get for this one, please. Calculate that. Yeah. It's not? Which one? This one?
Yeah.
What is it? is 15.
Yeah.
0.015. Ah, rats, thanks.
And that's
So then, of course, that changes the outside number, doesn't it?
That makes sense.
0.935. I thought you checked this for me, Mo.
I did the second part, didn't do the first part.
Ah. Oh, okay, yeah, okay. Okay, have you got this calculated yet?
Yeah. 0.75.
0.75? Okay, let's have a look. So on the top is cystic fibrosis and pneumonia. That's 0.045, and on the bottom is
0.06.
0.06, and you're saying this works out to be 0.75.
75.
isn't it 0.015?
Oh yeah, because we changed the number, didn't we?
No, but it's X. It's both, right?
Yeah.
It's.
Oh yeah, no, that's right. 0.045,
Yeah.
cystic fibrosis and pneumonia
Over
over pneumonia,
0.06.
and that's, you said, a 75%. Yeah, okay. What's wrong? I'm using this formula.
Yeah, I know, but I thought we found that the probability was 0.05.
Oh, that's just for this part of the Venn diagram, not for both. All a P. Yeah, no, Venn diagrams. Okay. Continue? Yeah. Anyways, the point here is that if somebody, in this scenario, if somebody presents with pneumonia, they've got a 75% chance of having cystic fibrosis, which means you would be justified in testing for cystic fibrosis, because it's more likely than not. Yeah. Okay. So since we're talking a little bit about tests, a little bit of vocabulary. So you might remember we did an example of. Let's have a look here if I can get real life numbers. Remember some time ago we did an example of a person takes a test and it tests positive, and we want to know how likely it is that they have the disease. Yeah, and I think we mentioned some language there, false positive and false negative. So does anybody remember the false positive? False positive. What does that mean?
Like someone has the disease, someone doesn't have the disease, but the test says it.
Okay, let's go with Mo.
Someone that doesn't have the disease, but the test said
That they did.
that
Okay,
yeah.
okay, fine. So this is wrongly given a positive for the disease, when in fact you don't have the disease. False negative then, of course, is the opposite. This is wrongly given a negative result for the disease. When you actually have the disease, you were wrongly told you don't have it. A little bit more vocabulary. This is called a type 1 error, and this one here is a type 2 error. And we were talking about which is worse. So which is worse? Yeah, type 2 error. It's much worse to be told that you're okay when you're not. The only thing that's bad if you're told you have it when you don't is then when you get follow-up treatment, it's discovered you don't have it. Okay, so we're quite tolerant of this, but not really of this one. Yeah. So as I was saying, the problem with a lot of tests is that it's not perfect. So I'll give you a small example just to get warmed up. So I tell you that the probability that somebody has the disease, so let's make this disease 10% of the population. No, that's quite a lot. 5%. 0.05. Okay, that's one piece of information. You have a test, and the test tells you you have the disease. Given that you have the disease, 99% of the time. So if you have the disease, then you will get a positive test result 99% of the time. And then the other part of the test is if you don't have the disease, the probability of getting a negative, we'll make that a little bit different. We'll say that part of the test is 98% good. So 98% of the time, if you don't have the disease, you'll get a negative result. So my question is, what is the probability that you have the disease given that you got a positive result? Now you can think about this as Venn diagrams as well, if you like. So here is disease and here is positive. Oh, and by the way, negative means not positive. So if you're not in this set, what does that mean for your test results? It's negative. And if you're not in this set, what does that mean? You don't have the disease. So people here, for example, what happened to them? They don't have the disease and negative results. So I'll put that in green actually. This is a good place to be. Where else is good? Good-ish. If you have the disease and you tested positive. This is good. If you're here, what does this mean? This means you have the disease and yeah, you get a negative result. That we agree is quite bad. And then what about here?
Tested positive, but you don't
False
have it.
positive.
Yeah, false positive. You don't have the disease, but you got a positive result. So how about I put that in blue? Not quite as bad as here, but it's certainly not green. It's not good. Okay. So you can fill this in and then use the formula if you like, or you, if you want, you can do it other ways. But why don't you try to fill this table in? I've given you enough information here, so do your best and then tell me what the answer is for this part. And while you're doing that, I'll try to get some real life test result numbers here. Now you do have enough info here because in the last example, how many pieces of information did I give you? I think I gave you 3 as well, didn't I?
Yeah.
Yeah, so you should have enough to finish the Venn diagram. Wrong answer. Do we need another minute? I still, still see people writing. Yeah.
So how do you get the positive sides?
Will we have a look at this now?
Yeah.
Yeah, well, we try, let's just see what happens if we try our same trick as before. So, could we do that trick as before? If I call this x, yeah, then we can kind of know this. What would it be? 0.05 minus x. Now, we have a small problem, I think, or rather, it's more harder than the last one. We can't quite do the same thing here, can we? No. Now, let's just look at what these represent to get a little bit of guidance. So, positive given the disease, that's the probability of positive and the disease, which that's the x here, all over probability of the disease. Now, this actually looks, it doesn't look like I need to finish anything else on the Venn diagram, because this here is x. There it is there. This here, we know it's 0.05, and we also know what this is supposed to equal, 0.99. So we can get this equation. We can get x over 0.05 equals 0.99. Okay, so this is looking good. What did we get for x here? 0.0495. Let me fill that in. 0.0495, and then what's, one sec, we'll fill that one in. 5 times 10 to the minus 1.
Minus 4.
0.0005.
Yeah.
It's quite a small number. Okay. Let's continue. So, have we used this piece of information yet? We haven't. So, what does this one represent? Let me put it here. That's negative and not the disease. So, that would be here. Let me call that y. Okay? The formula says it's y over probability of not having the disease. Now, we actually know what the probability of not having the disease is. What's the probability of having the disease? How many people have the disease? 5%, yeah. So, if 5% of the people have the disease, how many don't have it? 95. So that's 95. And this should equal 0.98. So again, by multiplying across, we can get the y. So what's the y here? For this one? 0.91? 931. Okay, good stuff. 0.931. And finally, what's the best way to get the number here? Everything adds up to 1. So if you just take out the calculator and do 1 minus 0.0005 minus 0.0495 minus 0.931, hopefully that's positive. And what do we get? No, I don't think so. What is it? 0.019. 0.019. Do you have pneumonia? Because there's a 75% chance you'll also have cystic fibrosis. That's a fun fact for you. 0.019 then. So now we can answer the question I wanted here. What's the probability that you have the disease given that you test positive? That's disease and positive. So what's disease and positive here in this? 0.0495 over positive.
0.0.
And that's 0.0495 plus 0.019, whatever that is. So do you have that calculated, Mo? 0.0495.
Horrible number. 0.72262.
7, 2,
2,
yeah.
6.
Okay, so if I do 3 significant figures, that'd be 0.723, or as a percent, 72.3%. So in this little example, if you tested positive, there's a 72% chance that you have the disease. Not a 100% chance, a 72% chance. Yeah? Ah, here. This is negative test result and not having the disease. So remember the formula is this: negative and no disease over no disease. So negative and no disease, I think I just called that the letter Y, which was this thing here. And no disease is 95. And we know that that's equal to 98%. So that's how I got this equation. Yeah?
So they specify always if you want the percentage of a decimal in the exam?
We don't usually care for the probability one. The word you just need to be careful for is exact. So if they say exact, do they want a percentage, a decimal, or a fraction?
Fraction.
Fraction. Yeah. If they say exact. Yeah. Let's get some real life data here. I think I should give you another one of these to try though. These are common in the exam. You can kind of see why. Well, I don't know if they always make it a medical one. But anyways, if you do any kind of statistics in science at 3rd level, you'll definitely be doing this again. I mean, it doesn't matter if you're going to do medicine, pharmacy, whatever. At some point you'll have a semester of statistics and this is bound to be in it. So I'll give you another example to try, a little bit of a different one. So we have 2 bags, we'll say, A, or 2 boxes maybe, A and B. And in one of the boxes, and you don't actually know which, so I won't bother calling them A. We can call them A and B, but I don't know which way around they are because you can't see inside the box. So one of the boxes has 2 reds and 1 blue, and the other one has 2 blues and 1 red, and we can you can call them A and B if you want, it doesn't matter. So what happens is, that's the background story, so to speak. So you come along, there you are, and you take one out, and it's a red one you take out. Now you don't know which box is which, you can't tell which is which, you can't tell if you have box A or you have box B. You took a red ball out. Now if you had box A, and you took a red ball out, you could take another red ball out, right? If you had box B and you took 1 red out, could you take another one out? No. So the kind of the question here is, given that you took 1 red ball out, how likely is it that you'll take another red ball out? Now you don't have to use Venn diagrams here for this. Perhaps this question you'd prefer to think about it as a probability tree, because there's a sequence here. You know, you take one out, and then you take another one out. That's fine too. But the question is kind of simple enough. What is the probability that you'll get a second red, given that you got the first one to be red?
It's different for both boxes.
Yeah, and you don't know which box you have, so you need to do a bit of thinking about that.
Do both?
Oh no, I won't tell you now. We'll see it in a moment. So that's the question. What's the probability that the second one is red given that the first one is red? We'll see. Calculate. Yeah.
Question. Will you put the first rate back to the box?
No, you don't put it back. You take it out and it stays out. Yeah. No replacement. No replacement.
Sir,
Yeah.
when he picks the second red, is it from the same box?
Oh yeah. Yeah.
Okay, that's easy.
Yeah. Just to be clear, he has two boxes. He takes a red out, and he wants to know how likely is it if he puts his hand back in, he'll take another red out. So obviously, if it was this case, then that's not going to happen.
It's just
But if it's this case, then you've got a 50-50 chance. So okay, you got this? No? Yes? Maybe. Yeah? So, let's have a look at this. Probably that the second one is red, given that the first one is red. So that's the probability that the second is red and the first is red, all over the probability that the first is red. Now, I think this is a good example of where using the tree will be better for this conditional probability, because the question is kind of more naturally thought of as a process. You first do one thing and then you do another. So we'll start off with, he can either pick box A or box B. And that's a half and a half. Yeah? Yeah?
yeah.
And then after, so, oh, wait. Okay, that's close enough. You're getting attendance for the second class, of course. Yeah. Right, what was I saying? Oh yeah, so if he picked box A, what's the probability that he'll get a red and a blue? So a red would be 2 over 3 and 1 over 3. So the probability of another red?
1 over 2.
1 over 3?
2.
1 over 2. And a blue? 1 over 2. And if you picked a blue, what's the probability of getting a red?
1.
1. And getting a blue?
0.
0. Okay, now let's look at box B. He can pull out a red or a blue. So red is 1 over 3 and blue is 2 over 3. Now if he took out a red, what's the probability he'll get another red here?
0.
Very good. 0 and a blue?
1.
1. And then here, if he pulls out a blue, what's the probability that he'll get a red?
Half.
A half and a half then. Okay, let's try and figure out what this one is. The second is red and the first is red. So you've got The second is red. Oh, so they're both red. So you can go this path, or you can go this path. But that one, yeah, that one's interesting because what's the probability along this path?
0.
0, because you're multiplying by 0 at the end. 0. And what's the probability along this path? 2/3 by a half by a half. It's 1/6. Thank you. So if you add them together, what do we get? 1/6. Over. Okay, what's the probability that the first one is red? Well, how many ways can we do that? So we can go A and a red, or B and a red. And I don't actually care about the rest of the tree, because I'm just looking up to the first one. So A and a red, what's that? That's a half times 2/3, what's that? 1/3. And then the other one, a half times 1/3? 1/6. And if I add them together, what's that? A half. Yeah? So this is equal to 1/6 over a half, which is equal to 2/6, which is 1/3 then. So there's a 1/3 chance that the second one you take out would be red. I wonder how many people got that. You got 1/3, but you felt it was wrong.
I didn't do it this way.
Did you use Venn diagrams?
No, I just used the probability. Like how you used to teach us before. Without the tree, but it's the same I can do on
The table?
No, it's just without the tree, but the same thing. So like the first wall is 1/3, the second wall is 2/1/2, and then I just multiply it.
Okay. I hope you didn't get the right answer just by coincidence.
I think I did.
Okay. Okay. It's good that you can see that.
Should
Yeah.
first red be 2/3? No, 1/1.
The first red?
Yeah, half. How should we get half?
I just.
A half?
Yeah. For
Where?
first red, you got 1/6. I understand, but 1/2. How'd you get that? Is that over
What was my 1/2 I wrote? Sorry, that was 1/3 plus 1/6 is 1/2.
Yeah.
Yeah, so you can have A and red or B and red. That's that there.
We care about the first time.
My bad.
Yeah. Okay.
Sir.
Yeah.
What if we meet some problems that contains a big size of sample, like 1,000 sample?
We'll be looking at that later. Yeah. Yeah. Okay, I'll just give you one more little conditional probability question to try, and I'll make it I'll make it a realistic one because I have some actual numbers here. Can I scroll down? Yeah. So here I'm looking at some. Oh yeah, so just a little bit of vocabulary. The sensitivity and specificity of a test. So the sensitivity of a test is how good the test is at giving you a positive result if you have the disease. So that's called probability of a positive result given that you have the disease. Yeah? And you could probably guess what the other one's going to be given the context. So what do you think the specificity of a test is?
Disease with
Probability of?
disease with
No. Negative test result given that you don't have the disease. And would we like these to be big or small numbers? Big. In a perfect world, we would like this and this, wouldn't we? In a perfect world. 100% of the time, you're told a positive result when you have the disease, and 100% of the time, you're told a negative result when you don't have the disease. That would be perfect, but of course that can't happen. So in this particular example, the disease is being pregnant, and the test result is the, well, you know, I'm not saying it is, it's just saying for this definition it is. Serum beta HCG test. So I have it here. This test is 100% specific, which is really good. It means if you're not pregnant, 100% of the time it'll tell you you don't have the disease. And then this one here is 97% sensitive. Okay. Now, I need to give you a third piece of information, something about the population, like how many people have D. But what I rather would like you to do, this isn't really an exam question, this is just more for your own sense of how tests work. I want you to calculate what's the probability that the person is pregnant given that they got a positive test result. And you have to estimate at least one of the probabilities. I'm just not going to tell you. So I think you'll have to estimate. I'll let you estimate, use your own judgment for what you think this is. I think in the previous example I told you this, didn't I? So I'll let you estimate it. Just think about populations and what you think this might be. Okay? Because another thing about probabilities, not for the exam, but just for real life, you don't always have all the information in it, you know? Like for example, suppose there was a new disease and we have a test for testing this new disease. It's possible we just don't know how many people have the disease because it's new. So you might have to estimate it. So you might say, well, I think it's less than 1% of the population because if it was more than 1% then there'd be more people coming to the clinic, you know? So I just let you use your own judgment to make an estimate here. We'll see what answers you can come up with, okay? So calculate this and you'll have to estimate, just pick your own number for what you think is realistic for this. Your choice, okay? I'll give you 2 or 3 minutes for that. answer yet? Right, let's have a look at this one now. I think there should be enough time. So let's draw our Venn diagrams again. Okay, I'm curious to what number people estimated here. So what numbers did people pick?
3%.
How many?
3%.
3%? 15%? Huh? 30%? Good, okay. What do we think? Now, it's very, very important here that you think about exactly what's happening. I know that at least half the population should be always not pregnant. You can guess which half. So, when we think about this, we need to be thinking about exactly what the universe is here. The universe isn't the entire population. What precisely is the universe here? Yeah, but actually you could even narrow it down a bit more than that. Yeah. Well, they have to be at least a certain age and at most a certain age, right? Yes. So, when you think about the possible people who will be taking this test, perhaps 15% would be a reasonable number of the percentage of people pregnant who would be in this situation of taking the test. So, you think so? Like, the question you got to ask yourself is this. Think about people who go to the pharmacy to buy this test. How many of them would actually be pregnant? 1 in 6 seems like a reasonable number.
You can use the birth rate to replace it.
Well, I mean, there's many things you can do to improve this. You could look at the birth rate, the population size, how many people buy pregnancy tests, you know. But just as an estimate, like, think about it. Which is more likely? If you know, 1 in 6 people who buy a pregnancy test are pregnant, or 1 in 60, or 1 in 600. 1 in 6 seems like a reasonable number to me. Or 1 in 5, something like this. Yeah. So we'll go with 15% here. 10. If you gave an answer between 10 and 20, maybe up to 25, that'd be good. Less than 10, I feel like is too small. Because, you know, if you said 5%, then you're saying only 1 in 20 women who buy a test are actually pregnant. So I think 15 seems like a reasonable number here. So we'll call this positive, and then here pregnant. So in the middle again is X. Okay, so let's look at this one here first. So let's turn this into an equation. So what's the equation here? Positive and pregnant, so what's that? X over pregnant, which is 0. What did we say? 15, isn't it? Yeah, that's what we said. And that should equal 97. Now, I won't calculate this because you all have different numbers. I just want to make sure that you had the right idea. So this is one equation. And that's an X there. That gives us X. Okay, let's look at the second equation here. So what's on the top? Negative and not pregnant. So that's here Y. So that's Y over how many people are not pregnant? 0.85. And what should this equal? 1. And that's interesting. That gives me the Y straight away. What's the Y here? Okay, so actually I will calculate 0.85. And did anybody get the X here? Say again? 0.1455. Good, good. Okay, so what's left to get then? Oh yeah, so this is 0.0045. And then you add them all up and take it away from 1. We can get the last one here. What's that? So 1 minus 0.1455 minus 0.0045 minus 0.85. So it's 0. Yeah, okay, 0 then. Well, this test is rather unusual because one of the parts of it is 100%. So what's the probability that you're pregnant given that it's a positive result? So that would be 0.1455 over positive result. What's that? 0.1455. So this equals 1 here. So for this test, if you are positive test result, then the conclusion is must be pregnant then. Okay, so you can see why I had a list of tests. This one was listed on the top as the best one. 97% and 100%. The worst one is, yeah, there's one here which is a 9% and a 97%. There's another one here which is 84.94, and then 76.93, 39.85, 88.42. Yeah. Yeah. Okay. So this one, apparently, this is the best one. I don't know why. Is it? Yeah. The people who, this is 97%, but I can see here on this paper, when they actually tested it out, the test actually did better than 97% here. It was actually 99.2. So it's this one's the closest you can get to 100% and 100% for both. Okay. All right. So they're all very much science bio examples there. Yeah.
Why did you divide it over 0.1455?
Is that not test positive?
Yeah.
0 plus 0.1455?
Yeah, but should it be over 0.15 because you're taking the probability of all of who's pregnant, right?
This is, oh, here it is here. This is positive.
Yeah.
So that's 0.1455 plus 0.
Yeah, I understand.
Yeah?
Yeah, I understand. But it would be over positive. It would be
over this. On the top is this number. On the top is this number, and on the bottom is this number. Yeah, yeah. Yeah? It's just in this example it doesn't matter because they're both the same, if you got the right answer. Okay, so there's some questions there. I'll let you try just for 5 minutes, and then we'll go on to the next lesson is very, very easy. It's very short. So yeah, try these for 5 minutes, and then we have one short lesson after that, and then on to statistics. So that leaves the probability for a moment, okay? So try that for 5 minutes there. Can I close this? Yep.